Hi everyone, this is a short 20-minute summary of our tutorial titled Mining of Real-world Hypergraphs, Patterns, Tools, and Generators. In this video, we will cover the outline and the motivation of our 3-hour tutorial. In real-world scenarios, how do we interact with others? Let's first think of publishing a paper. We often co-work as a group with lab members, advisors, and colleagues. And such collaboration of a set or a group of multiple researchers can be any size, which means that any numbers of researchers, including only two, can co-work together and form a group. For example, these are some of the papers that will be introduced in this tutorial, and you can see that each paper is co-authored by different numbers of people. We also communicate as a group in online chatting platforms such as WhatsApp or iMessage. We usually belong to different chat rooms consisting of groups of various people. It can be our friends, family members, or a project team. We can also think of buying a set of items in online e-commerce websites like Amazon. We add multiple items to our shopping cart and order them at once. Such set of items can be considered as a group of items that implicitly interact with each other. And similarly, we can find sets of tags attached to questions in online Q&A sites like Stack Overflow. These tags are indirectly related to each other since they are attached to the same question. So we can think such set of tags as a group interaction. So we have just seen some examples of group interactions that arise in many areas in our lives. Such group interactions among individuals or objects can be modeled as a hypergraph. Hypergraphs consist of a set of hyperedges, which are subsets of any number of nodes. So each hyperedge indicates a group interaction among its members. Let's see an example of 9 authors and 4 papers that were published by some of the authors. These collaborations can be modeled as a hypergraph on the right-hand side, where each node is an author and each hyperedge is a paper co-worked by the authors. So for example, the hyperedge E1 represents the KDD paper in 2005 by Jure Leskovac, John Kleinberg, and Christos Balossos, which is about the densification laws of real graphs. Also, notice that hyperedges can be arbitrarily sized. For example, the size of the hyperedge E3 is 4, while others are 3. Then why do we have to use hypergraphs to model group interactions? In other words, why don't we use graphs, which have been a prominent research area for decades? We can easily find the reason from this simple example. Consider a group of co-authors publishing a paper. How can we model this group as a graph? What people usually have done is to connect every pair of authors in the group and make a clique or a fully connected graph. So here, the 3 authors form a 3 clique, which we call a triangle. However, this simple reduction to pairwise relations loses group information. This means that from the graph in the right-hand side, we are not sure whether there was a group interaction among the 3 authors. Instead, every pair of them might have collaborated to publish 3 papers. From this example, we can see that since graphs can model only model pairwise relations, they cannot properly model group information. In other words, we cannot accurately recover the group information from pairwise graphs, so we can say that there is an information loss during the transformation into graphs. From the previous example, we have just discussed the inherent limitation of graphs, from which we find the reason to use hypergraphs to model group interactions. However, hypergraphs are not only conceptually beneficial, but recently they have shown to be powerful in various applications such as classification, ranking, link prediction, and anomaly detection. In this work, it has been demonstrated that solving such tasks using hypergraphs gives better performance than using graphs. And some of you might think that group interactions can also be represented as a bipartite graph. In this way, we can represent the group interactions without losing any information. However, modeling group information as a hypergraph poses new questions that are overlooked for graphs. Specifically, a hypergraph is a set of sets, and from this fact, we can analyze the data in a new perspective, which we share in this tutorial. And fortunately, here are many real-world hypergraphs datasets from various domains, including the examples that were shared in the previous slides. For example, a set of email receivers can be modeled as a hyperedge, and sets of substances that make up drugs can be represented as a hypergraph. And these datasets are publicly released by Austin Benson from Cornell University. And these are the basic statistics of the datasets. We can see that there are hypergraphs with different numbers of nodes and hyperedges. And basically, these hypergraphs are given with temporal information, which means that the time of the arrival of each hyperedge is given. But for static analysis, we can simply ignore the temporal information and transform them to static hypergraphs as well. These are some of the other data sets that are released. And also, there are many open source implementations for mining and generating hypergraphs. These are the GitHub links to the models that will be covered in this tutorial. So in this tutorial, we will cover 3 parts. First 2 parts will be about structural patterns of real-world hypergraphs. In part 1, we will share static patterns, and in part 2, dynamic patterns will be covered. And for each part, we divide the patterns into basic and advanced patterns. And in the last part, we will discuss generative models of hypergraphs. These models either generate the entire hypergraph or the sub-hypergraph. So the outline of part 1 and 2 is as in the table. 12 and 9 patterns will be covered for static and dynamic patterns respectively. And for each part, we divide the patterns into basic and advanced patterns based on their structural levels. So specifically, node hyperedge and hypergraph level patterns will be basic patterns, and sub-hypergraph level patterns will be advanced patterns. In part 3, which will be about generative models of hypergraphs, we will cover 9 papers. The models are divided based on whether they generate the entire hypergraph or the sub-hypergraph. Also, these models can be divided based on whether they generate static or dynamic hypergraphs. Then why are these important? Understanding the structural patterns and designing generative models that work based on them give insights into the hypergraph formation process. This can be used in various applications. For example, in predictions, by analyzing how the hypergraph evolve over time, we can predict future group interactions. In anomaly detection, if the pattern of some nodes or hyperedges do not follow the patterns that are commonly observed in the hypergraphs, then we can suspect them as anomalies. And for simulations, we can test our new hypergraph algorithms in many synthetic hypergraphs generated by the models, or we can run the algorithm in smaller hypergraphs by sampling from large ones. So in the first part of this tutorial, we will share some basic and advanced patterns that have been discovered in real-world static hypergraphs. For example, how many groups does a person belong to? How many people are in each group? Or how many people belong to 2 groups at the same time? These questions, which are quite simple and intuitive, are some of the questions that are going to be answered for the basic static patterns. Various work have revealed patterns that are shared across real-world static hypergraphs using different tools. For example, distributions of node degree, hyperedge size, and hyperedge intersection size of real-world hypergraphs have been found to be heavy-tailed, as shown in the figures. For the advanced static patterns, we will try to answer to more complicated questions. For example, how do 3 groups share entities? One of the good tools to analyze such patterns of hypergraphs is hypergraph motifs, or H motifs in short. As shown in the left-hand side figure, H motifs describe connectivity patterns of 3 connected hyperedges. There exist 7 subsets among 3 hyperedges as in the figure, and H motifs describe the pattern by their emptiness. In fact, there are 26 different types of H motifs, and we can count the number of instances of each H motif of the given hypergraph. As shown in the right-hand side figure, we can see that the distributions of the significance of each H motifs are very similar between hypergraphs that are from the same domain, but very different between those from different domains. And this implies that H motifs effectively describe the local connectivity patterns of real-world hypergraphs. We will cover the details of H motifs in the tutorial. So in the main tutorial, we will cover more patterns from different levels with details. Those highlighted in yellow are what we have just briefly covered, but in the main tutorial, 8 basic and 4 advanced patterns will be discussed. In part 2, we will investigate how real-world temporal hypergraphs are structured. Temporal hypergraph is a hypergraph consisting of temporal hyperedges, each of which consisting of a set of nodes and the timestamp it appeared. So temporal hyperedges consisting of the same set of nodes can appear at different timestamps. Specifically, we aim to answer to the questions, how do real-world hypergraphs evolve over time? And given a dynamic hypergraph, how can we analyze its structure? Let's see one of the patterns that will be covered for basic dynamic patterns. For the basic dynamic patterns of real-world hypergraphs, one simple question we can think of is, are groups likely to repeat the previous ones or to form entirely new groups? The answer to this question is yes, as we can see in the left-hand side figure. The x-axis represents the size of the hyperedges, and the y-axis is the ratio of the hyperedges that are repeated, and each color represents different datasets. It is observed that in real-world temporal hypergraphs, hyperedges tend to repeat previous ones, and this is strongly observed in small hyperedges. Then, do groups repeat old ones or new ones can be the following natural questions. The answer to this question is on the right-hand side figure. The x-axis represents how recently the previous hyperedges appeared, and the y-axis represents the similarity between the new hyperedge and the previous hyperedges. We can see that the similarity with the recently appeared hyperedges is typically larger than that with old ones, implying that hyperedges in real-world hypergraphs tend to repeat recently arrived hyperedges. Now let's see an example from advanced dynamic patterns. Here we want to see how 3 people in temporal hypergraph interact together. Given 3 nodes, we call closed triangle if there exists a hyperedge that covers the 3 nodes, and we call the appearance of such hyperedge as simplicial closure of the 3 nodes. This is distinguished from open triangle, where every pair of the nodes have interacted together in some hyperedges, but they have not co-appeared in a single hyperedge. Then, how can we predict the simplicial closure of 3 nodes? There are several factors that help predict the simplicial closure, but one of them is the density of the 3 nodes. On the right-hand side figure, 2 types of connectivity patterns of 3 nodes are compared in x-axis and y-axis respectively. And the values represent the probability of the simplicial closure, and each dot in the figure represents different datasets. We can see that triangle on the x-axis induces the 3 nodes to the simplicial closure compared to wedges, which have weaker connectivity. This means that the 3 nodes with higher edge density are more likely to have simplicial closure in the future. The outline of the second part of the tutorial is as in the blue one. The highlighted ones are what we have just covered, but in the main tutorial, more patterns with details will be discussed. In the last part of this tutorial, we will share some generative models of hypergraphs that preserve structural patterns of real-world hypergraphs. So first, we will introduce models that generate the entire hypergraph, and next we will share sub-hypergraph generative models. And most importantly, these models can explain why the aforementioned patterns occur by providing potential underlying mechanisms of them. Moreover, generated hypergraphs can be used for various purposes. So for example, we can produce hypergraphs with any size. For example, we can make a large-scale benchmark dataset, especially when real-world hypergraphs are hard to be collected. We also can anonymize the hypergraph with sensitive information by creating a similar but synthetic hypergraph. Another usage can be simulating hypergraph algorithms in a small but representative sub-hypergraphs. So for example, how can we reproduce realistic overlapping patterns? In other words, how can we generate hypergraphs that preserve various structural properties that are covered in part 1 and 2? For example, preserving the degree distribution can be one of our basic goals. HyperCL is a null model that generates hypergraphs that preserve the degree distribution. However, it fails to reproduce realistic hyperedge overlapping patterns as shown in the figures. HyperLab is one of the models that addresses the limitations of HyperCL and generates hypergraphs with realistic structural patterns. For example, in the figure, we can see that HyperLab accurately reproduces the degree distributions of pair and triple nodes of the real-world hypergraphs, while HyperCL fails. In this tutorial, we will cover various hypergraph generative models, including HyperLab. Rather than generating an entire hypergraph, or hypergraphs that are even larger than the original hypergraph, sampling a small sub-hypergraph has various benefits. For example, we can rapidly simulate an algorithm in a smaller hypergraph, and it is also useful for graph visualization and stream processing. So our goal is to generate a representative sub-hypergraph by sampling only a small number of the hyperedges of the original hypergraph. The term representativeness can be quite ambiguous, but it simply means that we want the sub-hypergraph to preserve the structural properties of the original hypergraph. Some of you might think that randomly sampling the hyperedges at uniform may be the solution. However, this yields to an extremely sparse sub-hypergraph which hardly reproduces the original structural patterns. MIDAS, which is one of the methods we will discuss in this part, is designed to sample a representative sub-hypergraph as shown in the right-hand side figure. A sampled hypergraph by MIDAS preserves the degree distribution of the original hypergraph most accurately, and we will show how MIDAS reproduces other patterns as well in this tutorial. So in the last part of this tutorial, we will share various generative models of hypergraphs. The generated hypergraphs are either full or sub-hypergraph, and they can be static or dynamic. So in conclusion, hypergraphs effectively model group interactions in complex systems. It provides a new perspective of set of sets, and from this fact, various structural patterns that are overlooked in graphs have been revealed. In this tutorial, we will share mining tools for analyzing real-world hypergraphs and generative models which explain why such patterns occur in real-world hypergraphs. Specifically, hypergraph generative models have various applications, including statistical testing, anonymization, and benchmark data generation. This short talk was a summarized version of the 3-hour tutorial, and more patterns and models with details will be covered in our tutorial, and the slides or other information can be found in our webpage. Thank you for watching our video.